Related rates. What if we're blowing up a balloon? Let's think about the things that are changing over time. Well, the diameter of the balloon is changing, getting bigger. The surface area, the volume, those are all variables that depend on time. If we looked at a connection between two of those, the volume, if it's a spherical balloon, is 4/3 pi r cubed. Now, if we looked at the rate of change of the volume, it would be connected to the rate of change of the radius then, since there's a connection between the volume and the radius here. So if you knew the rate of one of these, you could come up with the rate of the other, because the rates are related to each other. Let's look at an example. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we've got the spherical balloon and we've got this diameter. Now this is changing over time, and let's see, the information we're given is the volume is increasing at a rate of 100 cubic centimeters. That's the rate of change of the volume. So dV dt equals 100 cubic centimeters. How fast is the radius of the balloon increasing? So they're asking us to find dr dt, the rate of change of the radius, when the diameter is 50 centimeters, so when the radius is 25 centimeters. I just divided that diameter in half to have the radius. Our variables are volume and radius. They're changing over time, so we want a connection between them, and that is the volume of a sphere is 4/3 pi r cubed. Now for some of these related rate problems, you'll need some kind of geometric formula. You may remember it from past math classes, you may not. You can Google them. We needed a connection between volume and radius here. Next thing we want to do is differentiate this equation with respect to time, t, because volume is a function of time and so is radius. So we have dv dt equals 4/3 pi. Now this r cubed is going to be a chain rule because it's r inside of a cube function, but r is a function of t. So we've got power rule, power out in front, decrease the power by 1, multiplied by the derivative of what's inside. The derivative of r, since it's a function of t, is just expressed as dr dt. Now what we were trying to find is right here, and here's how it's related to what we already know. So let's substitute in the pieces that we have, and then we will solve this for dr dt. So we have 100 equals, we can cancel these 3's, 4 pi, substitute in 25 squared, dr dt. Now this is 25 times 25, and 4 times one of the 25's is 100, so I can reduce that with this 4 and with one of these. And so I can solve for dr dt. It's going to be 1 over 25 pi, and our units would be centimeters per second. So our radius is changing by 1 over 25 pi centimeters per second. Let's kind of summarize the steps we took and talk about the steps we would take to solve a related rates problem. The first thing we'd want to do is draw a picture if possible, because that's going to help us see connections between the variables, and that's one of the big things that we're going to need to do in these problems. Then we need to assign variables to all the quantities that are functions of time, and then the given information will give us a certain rate and a required rate, the one they're asking for. So we're going to express that information in terms of derivatives. Then we're going to write an equation that relates the various quantities of the problem. And sometimes we have to use some geometry. We may have to do some substituting if there's too many variables. Then we're going to use the chain rule to differentiate both sides of the equation with respect to t. And then we'll substitute in the given information so we can solve for the unknown rate. Let's look at another example as we do these steps. A hot air balloon is rising straight up from a level field. It is tracked by a rangefinder that is on the ground 500 feet from the liftoff point. At the moment the rangefinder's angle of elevation is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay, our first step is to draw a picture. So we've got this hot air balloon rising over this level field, and the rangefinder is 500 feet from the liftoff point. So we'll put that over here, and this is 500. And the rangefinder's angle of elevation, so let me get the picture drawn and then we'll identify. We'll call this angle of elevation theta and the height of this balloon h. So we've got our picture, and then we've got our specifics here that we're going to do in just a minute. So name the variables that are functions of time. So we've got theta, a function of time, our angle of elevation is changing over time, and we got h, our function of time, our height is changing over time. Express the info and required rate in terms of derivatives. So let's see what information they gave me. At the moment, the rangefinder's angle of elevation is pi over 4. So when theta equals pi over 4, the angle is increasing at a rate of 0.14 radians per minute. So this is the rate of change of the angle, and that's 0.14 radians per minute. And then it says how fast is the balloon rising at that moment. So what we want to do is find dh dt. Next thing we want to do is write an equation that relates the variables. Okay, my variables are theta and h. How are they connected to each other? And as I look at this triangle, I'm seeing trig because I have opposite and adjacent. So the connection, the tangent of theta equals h over 500, or we could express that as 500 tangent theta equals h. So there is our connection between our variables. Differentiate this with respect to t. I'm going to go up and do this up here. So the derivative, I have 500. The derivative of tangent theta is secant squared theta, and then d theta dt, because of the chain rule, differentiating with respect to t, theta is a function of t, and that will equal dh dt. Substitute and solve. So now I'm ready to put in my angle theta and my d theta and find my dh dt. So dh dt will equal 500 secant of pi over 4 squared and 0.14. Secant of pi over 4, well, that's the reciprocal of cosine of pi over 4, which is 1 over square root 2. So when I flip that over, that's the square root of 2, and when I square it, that's 2. So all of this part is 2. 500 times 2 is 1,000 multiplied by 0.14, so I have 140, and our units are feet per minute. So this balloon is rising when the angle is pi over 4 at 140 feet per minute.